So this week is the last and final week of this Cyber Security 360. This week's topic is decoding by concepts, and he has been ready.
Krishish, can I start now?
Yes, brother, you can start.
Okay, thanks a lot, Rashid. See, now today we are going to learn as to how data is getting transferred on the network and how the data is prepared for transmission. And what is the role of protocols? What's the role of protocols in communication? We're also going to see as to how important it is to understand how the protocols interact with each other and then prepare the data for communication. So we're going to see today, at least one example we're going to see, the importance of understanding how the data is prepared for communication and how the protocols interact with each other, right? Now, what are protocols? We know that different protocols are there in network, like IP protocol. We have say TCP protocol. We have say UDP protocol. We have ICMP protocol. We have HTTP protocol. FTP protocol. There's so many protocols are there, right? Anything that is done on the network, on the system, is done by some protocol or other. Whenever any data has to be moved from one place to other place, it's the protocols that come into picture and then send the data to each other, or the protocols prepare the data for communication. So in security also, if at all you want to analyze if any attacks are happening, you can see, or you want to see as to what's the problem in the network, we normally try to do what? We capture the packets. We say we capture the packets, open the packet, see as to what is there inside. By analyzing the protocols, we do something called as protocol analysis. Protocol analysis. We capture the packets. By seeing the traffic pattern over there, we come to conclusion if any attack is happening or any problems in the network, now we try to see, right? So understanding about the protocols, how the protocols interact with each other, how the data is being transmitted on the network is very important to understand security itself. In networking, any study in networking has to start with understanding about the protocols. So what are these protocols? See, if at all I want to write a letter to my friend, I take the data, I put a cover on it, I write say to address and from address, and I go and then post it in the post box. Some postman will come over there. He'll gather from like this, he'll gather from different post boxes and he'll go and give it to the local post office. The local post office, they sort out all the posts and then they bundle them into different bundles depending on which part of the city that particular post is going. And then somebody will carry these bundles to say maybe to the railway station over there and then drop it over there. And that through the train or by flight, the post will go to some other city. Again, the main head post office there, somebody will sort out all this. And somebody will again come to the local, go and give to the local post office. And from local post, that post will go and deliver it to the individuals, right? So many people are involved in making the data go from one place to other place. That's what happens in real life. In real life, if at all I want to write a letter to my friend, I take the data, put in the cover, and post in the post box. If I'm sending by post, all these things happen. So there are so many people, or so many employees are there, employees employed by the postal department, trying to deliver the letter from one person to other person. All these are what? Postal staff. We have say postal staff trying to like say deliver the letter from one person to other person in real life. In the same way, when one system wants to talk to other system on the network, the system might be here somewhere in the world. The system might be somewhere else in the world. For example, this is like say facebook.com. This is like say facebook.com. So if I type here www.facebook.com, that means what? I'm trying to send some data from my system to some facebook.com server located somewhere in the world. So the data has to be transmitted from here to this place, right? As well as a postal staff trying to do it in real life, we have something called as protocols. We have something called as protocols trying to do the same thing in computer network. So you can imagine protocols like what? Different employees. As well as a postal staff, postman is there, the van driver is there, sorting person is there, right? All these are what? Employees of the postal department trying to send the letter from one person to another person, right? In the same way, we also have something called as protocols inside the computer systems who are trying to deliver the letters from the data from one place to other place. So you can imagine these protocols like employees trying to deliver the data from one place to another place. So before the post office also could send the data from place to place, the data is prepared for transmission, right? So we take the data, we write the letter, we put a cover on it, we write what? To address and from address we write, right? So the data is prepared for communication. The data is what? Prepared for communication here in real life also. I can't simply throw the letter. The letter has to be put in an envelope. On the envelope, I write what? To address and from address, right? Same way, before the protocols could deliver the data from one place to another place, the data again has to be prepared for transmission. So the data is taken, a cover is added on that with what? To address and from address. Here we add, let's say, to so-and-so, say to Farouk, say present in Birmingham, say UK. We write the address, right? The same way here also we write something called as an IP address. We say the IP address is, for example, 130.140.0.10 means the system identified by 0.10 located in so-and-so area. If I say to Farouk, present in Birmingham, present in UK, so-and-so person in so-and-so area. Now to go to this area, which is the route I need to take. Same way, so-and-so system in so-and-so area, to go to this area, which is the route I need to take. So routing happens because of something called as an IP address. So some address is there. Without address, routing is not possible. So the idea is, before the protocols could deliver the data from one system to other system, the data again has to be prepared for communication. Right? So only if you understand how the data is prepared for communication, which protocols come into picture if you're given any activity, and how these protocols interact with each other. If you understand all these, you understand something called as networking. So this is a core knowledge in networking. You should understand about what? For any activity to take place, which protocols come into the picture, and how the protocols prepare the data for communication, and how the protocols interact with each other to make the data be sent on the network. You should understand all this. Then you can understand what is meant by packet capturing. So if at all you want to troubleshoot the networking problems or solve the security issues, understand as to what is happening behind the scenes to either from security point of view or troubleshooting point of view or performance point of view, you need to understand how to do something called as protocol analysis. So we capture the packets, open the packets, and see as to what is happening behind the scenes. Or by seeing the traffic pattern when you capture, you understand as to what are the issues. So to capture the packets analyze, we have different tools are there. We have something called as Wireshark. Wireshark is a very popular tool which everybody uses in the networks. We also have something called as TCP dump. But all you try to, let's say, do on Linux, we have TCP dump. You can use the command line. We also say network monitor by Microsoft. Like that, different tools are there. What do all these tools do? These tools try to capture the packets and open the packets for us. So we can see as to what is present inside the packet, or we can see the traffic pattern, understand as to what are the issues. Right? So there's open source is there. We have like say like this. We have let's say some command line tools are there, graphical tools are different tools. But all the tools, what do? They capture that same packets and then give us the output in a readable format so that we can understand as to what is happening. So today I thought I'll show you a small example. Because I said just 1 hour class, I thought I'll show you one small example. Understand as to how to do captures. Also understand how the data is being transferred from one place to another place. You may need to know as to what is meant by an IP address. You also need to know what is meant by a hardware address. And what's the difference between IP address and hardware address, right? When you give the ping command, why do we give the ping command? And what is the protocol called ICMP doing behind the scenes and all you need to understand, right? So some prerequisites are required to understand this particular class, but also try to throw some light on the basics also as I show the demonstration. So what am I trying to do now? I'm trying to work with a small network. I've taken, let's say, 5 systems in the network. System A, system B, system C, D, and then E. I have, say, 5 systems here. And all the 5 systems are kept in the same network. The network ID being 10.0.0.0 with the mask 255.0.0.0. And I've said 5 systems like this with IP address 10.0.0.10, 10.0.0.20, 10.0.0.30, say 10.0.0.40, and 10.0.0.50. There are 5 systems here. All the systems are in the same network ID. The network ID being 10.0.0.0 and the subnet mask being 255.0.0.0. And all the systems have got something called Ethernet card. I kept Ethernet card on all the systems and I connected all this using something called Ethernet switch. So I use Ethernet cables and then connect the systems to the same switch like this. So all the systems are connected to the same switch like this. So what is the data link layer technology I'm using here now? I'm using something called Ethernet. So in other words, when 2 different systems want to talk to each other, there should be a vehicle to move the data from one place to other place, right? When 2 systems in the LAN are trying to talk to each other, say for example, the system is trying to send some data to other system on the network. So we need a vehicle to move the data from one place to other place, right? So which vehicle I'm using in this particular network here now? The vehicle is called as what? Ethernet. Ethernet is the vehicle I'm using to move the data from one system to another system in this particular network right now in our example. Are there other vehicles like Ethernet? Yes. So all these are called as networks. We have so many different vehicles are there. We have say Ethernet is one vehicle. We have say Ethernet. Ethernet is one vehicle we have. We also like say for example token ring. We may not use it anymore, but token ring also is there. We have say FDDI. We also let's say for example HDLC. We also have say PPP. We also have let's say for example frame relay. Like that, ATM, X.25. All these are what? All these are different vehicles that could move the data from one place to another place. All these are vehicles that could move the data one place to another place. See, now we have different vehicles in real life. We have say car is there, we have say bus, we have say flight, we have say ship. So many different vehicles are there, right? See, now if at all I want to go from my house to my say, center station, I may take a bus or a taxi. I don't take a flight, right? But if at all I want to fly from India to London, then I may take what, a flight? So some vehicles are meant for short distance travel and some vehicles are meant for long distance travel, correct? So in networking also, for short distance travel, we have vehicles like Ethernet, tokening, FDDI. We call them as local area networks. And for long distance travel, like say a router is talking some other router on the WAN link, then I may use a vehicle like all these. These are called as what? Wide area networks. The vehicle itself is called as what? Network. So underlying network moves the data from one place to another place. And there are so many different vehicles like this available in computer networks. Ethernet, tokening, FDDI come under what? Local area networks. Whereas HDLC, PPP, all these come under what? Wide area networks. So these are meant for long, short distance travel. These are meant for long distance travel. Right. So within my network, I have an office. The system in the ground floor is kind of system in the first floor. Then I may go for something called Ethernet. I may not use frame relay. I may not use all this, right? A router is there in India, talking to router in the ISP side. Then I may use, let's say, protocol like PPP protocol. So short distance travel, I use protocols like this. Long distance travel, I use protocols like this. All these are vehicles that move the data from one place to another place. So in our case study here, I choose vehicle called as what? Ethernet. I choose vehicle called as what? Ethernet. So how do I say my vehicle is Ethernet? I put Ethernet card in the systems. I use Ethernet switch to connect all the systems together like this. I use Ethernet cables to connect all the systems to the switch, all right? So the vehicle is what? Ethernet. Ethernet is a vehicle. So now, every day as a network engineer, we give this command called as ping, right? If at all I want to see 10.10 and 10.20 could talk to each other, we normally give the command called as ping 10.0.0.20. Ping stands for packet internet grouper. And I say I'm asking 10.10 to send to ping 10.20. Why am I trying to give the command called as ping? I'm trying to see if these two systems are could be communicating with each other. Could they communicate with each other? That's what I'm trying to check. See, now that means what could be the issues for these systems to talk to each other? What could be the problems? The problems might be many, right? There might be so many problems before these two systems could talk to each other. Some of the problems might be hardware issues. There might be some software issues also, right? What hardware issues you may find here? The NIC card may not be functioning properly. the cable is not crimped properly, the cable is, let's say, cut here somewhere, and I say the switch is not powered on, the port on the switch is not working. All this could be what? Hardware problems. Because of these hardware problems, system A and system B may not be able to communicate with each other. What could be the software problems? The software problems could be, for example, the IP address assigned to the system is not unique on the network. So IP address is not taken by the system here, and the system does DAD, duplicate address detection, to see if any other system has got the same IP address. Some IP conflict is there. So IP address is not bound to the NIC card. Or the TCP/IP protocol stack itself is corrupt. Or the device driver installed for this NIC card, the device driver is not also corrupt. Or the OS, some file is missing. The routing table, route did not get registered properly on the network. Like that, so many software problems also might be there before these two systems could talk to each other. Before system A and system B could communicate with each other, there might be so many hardware or software problems. What's the best method to rule out if any problems are there like this or not? How do I rule out if any problems are there? What I do? I send some sample data. If I send a sample data from A to B, B also can send some sample data to A. That means what? Everything is fine. I send some sample data from A to B, saying that, yeah, if you're available, please reply to me. System B also sends a reply. Means what? If the data can go from A to B, data also could come back from B to A. Means what? There's no hardware, no software issues are there on the network, right? So that's what I do when I give the command called as ping. A packet by name echo request. Echo request goes from A to B. Echo request. Packet by echo request goes from A to B, and a reply comes back in the form of what? Echo reply packet. If echo request can go from A to B, echo reply could come back from B to B, means what? No issues are there. So that's what I do whenever I give the command ping. To check if any connectivity issues are there, we generally give the command called as ping. Like all of you might be knowing about this already. But which part of protocol comes into picture when I give the command called as ping? A protocol by name ICMP. See, anything that happens on the network is done by somebody has to do it, right? If at all, like say I'm carrying the data from the place in real post office network also, some employee should be there. So anything that is done on the net is done by some protocol others. Which protocol comes to picture when I give the command ping? A protocol by name ICMP, Internet Control Message Protocol. And ICMP protocol has been developed to give clues. If at all any issues in the network, for example, I'm a network engineer, some problem is on the network, I want to do some troubleshooting, somebody has to give some clue, right? Only if at all I get some clue somewhere, then I'll be able to take the clue and then follow, understand, and try to solve the issue, right? So somebody has to give some clues in the network, right? Who is that protocol that is giving the clues to us to see if any issues are there? ICMP protocol. So ICMP protocol has been developed by the programmers of TCP/IP to give clues if any issue is there in the network. So automatically some clues keep coming. So whenever I use the commands, some commands I use to generate the clues also if any issues are there, right? So ping is one command that makes use of ICMP protocol. So whenever the command ping, ICMP comes to the picture and then sends a packet called an echo request. Now when ICMP, who's talking? When I give the command ping, echo request sent by system A to system B, echo reply comes back from system B to system A, right? How do you know it's an echo request packet only? How do you know it's echo reply packet only? The ICMP protocol packets are identified by something called as type number, and code number. So different ICMP protocol packets are identified by type numbers. For example, echo request type number is 08, code number is 00. Right? Echo reply type number is 00, code number also 00. Destination host is unreachable. 03 is a type number, 01 is a code number. In the 03 again, there are so many code numbers also there. Destination unreachable is one type. Why is it unreachable? Different reasons become different codes. So you should also know ISMP protocol thoroughly. You should understand what is the type number and code numbers for different types of ISMP protocol packets. Thing is only one command. Echo request, echo reply, only 2 packets. So many packets are related to ISMP, right? You should also know all this. So right now, when I'm trying to demonstrate, what? Echo request and echo reply. Echo request type number is 08, code number is 00. Echo reply type number is 00, code number also is what? 00. So what happens now? In our case study here, when the system is trying to, when I give the command ping 10.20 from 10.10, ICMP protocol comes into the picture here. And ICMP prepares the data, and the data looks like this. It is what? Echo request packet? Echo request. Echo request. So how does the data look like? It's an ICMP protocol data. In that protocol data, the type number is 08, code number is what? 00. This is the data. This data is being sent by whom now? The ICMP protocol on system A is sending this data to whom now? ICMP protocol on system B. But the data has to be prepared for communication, right? Whenever I want to write a letter to my friend, I can't simply give the letter itself. I should also put in the cover, because somebody else is going to carry the data from one place to other place. I need to put a cover, right? So I put a cover here. I put a cover. Who's going to put a cover? IP protocol. So what happens here? ICMP protocol here gives the packet data to whom? IP protocol. ICMP does not give to TCP. ICMP does not give to UDP. ICMP always gives to whom? No, IP protocol. So what does IP protocol do? Puts a cover on it. Where you have something, and IP will add always something called as to IP address from IP address. Who is talking to whom now? In our case study here, system A is talking to system B. System A's IP address is what? 10.10. System B's IP address is 10.20, right? So what will be the source IP address in this particular packet now? Source address will be 10.0.0.10. To address will be 10.0.0.20. So ICMP gives the data to IP protocol. IP puts a cover like this to IP from it. But then, who is the vehicle here which is going to move the data? Ethernet is a vehicle. Ethernet is a vehicle. And Ethernet understands something called as only MAC address. Ethernet does not understand IP address at all. Ethernet understands only something called as MAC address. Because Ethernet, let's say, if at all system is on system A, Ethernet does not go and give only to system B. Ethernet goes and gives to all the systems. It goes and gives to B, C, D, E. Saying that, do you want this? Do you want this? Do you want this? The systems open the cover, first cover, and see the second cover and see as to what is the MAC address over there. If the MAC address is matching their own MAC is meant for them. So systems understand as to what is the packet is meant for them only or not by seeing something called as MAC address, not IP address. See now, if at all I write a letter to my friend, what do? I take the data, I put only one cover on it. And there I write something called as to address and from address. But when two different systems are talking to each other, what do? They take the data, but then they don't put only one cover. They put how many covers? Cover upon cover. They put one cover, and they put second cover. They put what? Third cover, fourth cover, say fifth cover, say sixth cover, right? And then you have what? Seventh cover. So 7 covers upon covers are added like this. So something like an onion gets created. So I add only one cover if I want to write a letter to my friend, but systems add how many covers? 7 covers like this. These covers also got a name, and also a number. The numbering starts from outside to inside. First cover, second cover, third cover, fourth cover, fifth cover, sixth cover, seventh cover. We call it as physical, data link, network, transport, session, presentation, application. Now, where do I see the 2 IP from IP? Third cover. Third cover is called as network layer cover. That's where I see something called as 2 IP and from IP. Where do I see the MAC addresses? I see the second cover. The second cover is called as data link layer. That's where I see something called as 2 MAC address and from MAC address. So I see MAC addresses only if the vehicle is Ethernet. If the vehicle is not Ethernet, vehicle is, let's say, frame relay, then I may not see MAC address. I see something called a DLC numbers, DLCI numbers. Data link connection identifier numbers. Or if it's only PPP protocol is the vehicle, I may not see any address at all. I may not see any number at all. There's no need for any identification. Because a point-to-point network. Like the different concepts are there. Because in our capture here, the vehicle is like say Ethernet. I see something called as 2 MAC address and from MAC address. And MAC address is 48 bits in length, expressed in hexadecimal and all is also there, right? So the idea is when the data is being prepared for communication here. So whose vehicle here is going to move data from A to B? Ethernet. So IP gives to whom now? Another protocol called Ethernet. So what does Ethernet protocol do? Puts one more cover on it. One more cover on it. And adds something called as 2 MAC address and from MAC address. Right. So from MAC will be what? MAC address of system A. 2 MAC should be MAC address of system B, right? Ethernet understands only something called as MAC address. So when the packet goes in system also, what do? They open the first cover, then only they see the second cover, right? When the packet goes like this, what happens now? Systems will open the first cover, then only see second cover, right? So where do I see the MAC address? We see the MAC address. The second cover, I see something called as hardware address. Third, only we see something called IP address, right? So only if I open the second cover, first cover, second cover, third cover, only if I open the second cover, I can see what is a third cover, right? So when the packet comes in the system on Ethernet, this is meant for them only or not by seeing something called as MAC address, not IP address. So when Ethernet is trying to move the data here, so you should know what's the MAC address of all the systems, right? So what happens now? This packet cannot go as of now because I know my IP address. I also know the 2 IP because in the comments of this IP address. I know my own MAC, but I don't know the MAC address system. So what happens now? If I don't know the MAC address, then what happens? There's a protocol called as This packet cannot go. This packet cannot go as of now. And we say encapsulation phase. Encapsulation phase. So somebody has to find out the MAC address of system whose IP address is 10.20. Which protocol comes into picture now? A protocol by name R protocol comes into picture. And NARP stands for what? Address Resolution Protocol. It sends a NARP request packet. Now, if I see system A here, we have R protocol. R protocol gives the data directly to whom now? Ethernet. R protocol does not give to IP protocol. It does not give to TCP protocol, UDP protocol. R directly gives to whom now? Ethernet. So we see only Ethernet cover on this. You only see what? Ethernet cover we see, where you see something called as 2 hardware address and from hardware address. And the ARP request says, my IP address is 10.10. My MAC address is so and so. If your IP address is 10.20, what is your MAC? That's a question. ARP is asking ARP protocol on all the systems. But then this ARP request, see for example in the classroom, I don't know who is a Mohan. What's the best way to find who's Mohan here? I send a query as a broadcast. I send a broadcast saying that, who is Mohan? Please stand up. It goes to all of you process, and only one person raises a hand, right? Saying that I'm Mohan. The same way, When our protocol wants to resolve the IP address to MAC address here, what does our protocol do? It sends a broadcast packet to all the systems, saying that if at all is a system by IP address 10.20, please reply with your MAC address. It's a broadcast packet, but we said that the systems receive the packet, they open the first cover, they see the second cover. In the second cover, the MAC address is their own MAC, then only they process the packet, right? So in this case, how do systems know that it's a broadcast package meant for all the systems? So when all the 48 bits are ones, we reserved it for what? Broadcast at the address. So it turns out what? 12 Fs, because 4 bits in binary are equivalent to 1 digit hexadecimal. 4 Fs will come as what? F. So if at all I see 12 Fs in the 2 meant for, it is meant for whom? All the systems. So how do I see the ARP request packet now? If I see the ARP request packet here, I see the 2 MAC address will be what? 12 Fs. 12 Fs will be there. From MAC will be MAC address of system. Before the core request packet could go from A to B, somebody asked, because this packet cannot be sent because we don't know what is the MAC address. Somebody has resolved the IP address to MAC address. A protocol by name R protocol comes into the picture, sends a broadcast, and then tries to find out the IP address to MAC address, right? So once the ARP reply packet comes back, I get the MAC address. Then I fill up this field with what? MAC address of system B. Now I send the packet to all the systems. This time again, all the systems open the first cover. They see the second cover. They see the MAC address of B. So other systems do not process the packet. Only system will take the packet inside. It also removes the data link layer. Then this is IP cover. IP address is 10.20. Then IP gives to whom? No, ICMP. ICMP will know that ICMP is asking for a query because ICMP can replace back with the same flow again. Understand? So what I do now, let us actually do the capture and see the packets actually look like this or not. So in this case here, I have how many systems are there? No, I have here 5 systems connected like this, and all of them are in this folder IP address as shown in the diagram. So let's see that. So let us go to the lab setup now. In the lab, I have a system A here, right? So I go to system A here. In the system A, I give the command cd / I say clear the screen. I say IP config. What is my IP address? 10.10. Right. Similarly, I go to system B here. System B also I log in. So I go here, I go to the command prompt. There again, I say cd / clear the screen IP config. What is the IP address here? 10.20. So I go to system, I want to see a system 10.10 and 10.20 could talk to each other. I give the command saying what? Ping 10.0.0.20. I could ping, right? Echo request is able to go, reply is able to come back. I try to ping 10.30, I could ping. Can I ping 10.40 also? I could ping. Can I ping 10.50 also? I could ping. So all the systems are now able to talk to each other because they are all, let's say, no issues are there, either hardware or software problems are not. What I do, I am on system A here. I try to give the command ping 10.0.0.20. I want to see as to what is happening behind the scenes. So what do? I go to the programs here. I install here a tool called as Network Monitor. On Windows, you could install Wireshark also, but I'm using what? Network Monitor. So I bind it to this NSA card here. And I tell Network Monitor, start the capture. Start the capture. And the capture is going on. I go now, I give the command ping 10.20. I got reply, echo request is able to go, reply is able to come back. Again, I go to Network Monitor. I stop the capture. I say display the captured data. Show me what is captured, right? Maybe I can also go here. I can increase the font size so all of you can see properly. If you see carefully what happened, when I give the command ping here, I captured how many packets? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 packets are captured, right? And if you see here, this ICMP protocol packet I captured. When I double click on it, I open. We said ICMP is talking to whom now? ICMP protocol. When I expand ICMP here, I should see what? Type number and code number. So what's the type number here now? 08. What's the code number here? 00. If the type number is 08, code number is 00, it is what? Echo request packet. So ICMP is sending this particular data saying, if at all you're available, please echo back so I know that you are available. So I'm sending some packet called as what? Echo request packet. Now ICMP gives data to whom? No, IP protocol. And what does IP protocol do? It puts a cover, right? And what do I see in the cover now? I see something called as source address is 10.10. Destination IP address is what? 10.20. And we said that ICMP IP gives to whom now? Ethernet again. Ethernet I should see what? I should see the source MAC address is my MAC address. Destination is on MAC address system B. See now here, how do I know my MAC is AEAA? The last 4 AEA, right? So I go here, I say IP config /all. It shows that the physical address is what? The physical address is AEAA, right? Similarly, if I go to system B, there I say IP config /all. Again, if I say here, what is the MAC address of this particular system here? BC8D, right? So in the capture here, I could see my own MAC address here as AAA. I also destination MAC also BC8D. How did I find out the MAC address here? So before this echo request packet could go, a packet by name ARP request has gone, right? We said ARP resolves the IP address to MAC address. If I double click on it, how does ARP data look like? It looks like it says, my IP address is so-and-so, my MAC address is so-and-so. If your IP address is 10.20, what is your MAC address? Please reply back to this, right? And we said ARP is always a broadcast packet, where I see something called as to MAC and from MAC. The MAC is what? My own MAC address. Destination MAC is what? 12 levels. Means it's a broadcast packet. So when this ARP request is sent by the system here, it goes to all the systems. All of them remove the first cover. They all see the second cover. Destination MAC is what? 12 levels. It's meant for whom? All the systems. So all the systems process the packet. All of them understand that somebody is asking the MAC address of 10.20. So other systems keep quiet. 10.20 only responds back saying, my IP address is 10.20. My MAC address is so-and-so. And this is what? It is a unique aspect. That's why I see here, source MAC and destination MAC are individual MAC addresses. So once I get the ARP reply, so I know the MAC address system, that I use here as what? To MAC address and then send the packet. You understand? No? So like that, because I did not know as to what is the MAC address of system B, our protocol sends an ARP request, finds the MAC address. Because I already know the IP address, then I'm able to do like this, right? Now, what happens if I give the command ping www.amazon.com? I don't know the two IP address. So what should I do now? I should actually resolve the IP address to MAC address first of all, right? That time if you see the capture, you see a DNS query going from system B, reply coming back again. Then once the DNS reply comes back, now I know the IP, but I know the MAC address. Again, I send ARP request, get the MAC address, goes on like that. So only if you know how the protocols interact. See, in this case, what happened? ICMP always gives to whom? IP protocol. IP always gives to what? The data link. Could be Ethernet or PPSDLC protocol. ICMP does not give to TCP or UDP. And ARP also always gives to whom now? ARP does not give to IP. It always gives to whom now? Ethernet protocol, right? So if you know as to how the protocols, like say, which protocols come into picture whenever I generate any traffic, and how the which protocol is the protocol, only then you will be able to understand the concept properly, right?
நடந்துச்சு ஆஃப் பண்ண வெளியில வரும்
Okay. So like that, we have seen only one capture in this case. Like we can see many captures. They will understand the concepts, right? So in this case, I will test again 5 systems here. System A, B, C. I just give the command ping and try to understand some concepts in network. So, and if at all you understand, you want to understand security, it's very important to understand about what protocols. Protocols. Which protocols come into picture for any activity? This we need to understand. Which protocols come into picture for any event to happen, and how the protocols interact with each other. How they interact with each other. How they interact with each other. Who talks to whom? HTTP protocol gives data to whom now? Always TCP. TCP always gives to what? IP. IP gives to Ethernet or family dependent data link the packet goes. FTP gives to whom now? It gives always to whom? FTP gives to TCP. TCP again gives to what? IP. IP again gives to the data link. DNS. DNS queries. DNS gives to whom now? UDP protocol. UDP gives again to IP protocol. Right? So like that, if you know, when you generate any traffic, which protocol come into picture, how they interact with each other, and how the data is prepared for communication. Data is prepared for communication. This we need to understand thoroughly. Only then you'll be able to understand security. You'll understand security also. See as to what's happening in the scenes, and then you can say hey, security breaches are there. You can understand all these concepts, right? So with this more demonstration, I would like to, let's say, stop the class now. Any doubts you have, you can ask me. Then I'll hand it over to Quasar Rashid. Rashid, you are there, ma?
Yes, sir. I am there.
Yeah. Yes. I come to my discussion. Now you can open it for discussion.
So, do you have any question, guys? Like it's around 10 p.m. If you have any questions, you can post it here, and Mr. Koti will be answering them. If not, you can post it in the WhatsApp groups, and we'll try our best to answer it.
You can also unmute if you have anything else.
Yes, you can raise the hand or unmute and start speaking yourself.
Yeah, okay. Then we can close the session if there is no questions. Thank you, Koti, for the wonderful presentation. Thank you.
Okay, thanks.
Thank you very much, sir. We can end the session.